Hello. Okay, so I'm going to talk to you sort of about an experimental study we've been doing on trying to improve the sound transmission loss of a wall, specifically in the coincidence region. Has that moved? There we go. Okay, so the motivation of this project was kind of around the fact that obviously the densification, especially in New Zealand, of housing and populations in cities is growing. So we're sort of moving towards these apartments with intertenancy walls. And specifically in New Zealand and probably around the world, the cost of housing is going up. And we know that the impacts on the health and well-being of people with noise penetrating into the rooms is quite major. And also a lot of the systems we use, specifically in New Zealand, I think in Australia and in the US, are also similar constructions. Then a lot of the performance is sort of bound by the mass air mass resonance region and the coincidence region when walls are measured for their performance using STC and RW, which are sort of single figure classifications. So this image on the left is a typical transmission loss plot of a double leaf wall that we have in New Zealand, and you've got two specific regions. You've got the mass air mass resonance region at around 80 hertz, which can shift depending on the depth of the cavity and the weight of the leaves, and the coincidence region, which is shown in this plot, and it kind of starts around the sort of 2000 hertz region. So I'm going to specifically talk around the coincidence region this time. We have another project around the mass air mass resonance region, but for this talk we're just going to talk about the coincidence region. So the critical frequency is shown here, which is basically where you first start having that decline in performance, where the bending waves start to have an effect on the transmission loss. And this region is determined by the bending waves, where the incident wave couples with the bending waves in the material and allows easier transmission of sound through the material. And it's most related to the Young's modulus, or the stiffness and the thickness of a panel. So the thicker the wall. So I've got some plots here of some typical critical frequencies. So you can see that concrete, which is a very stiff
Hi,
material.
Andrew. I can't see anything. I don't think anyone else can.
Okay. Why is that? Is that since the start of the plot?
No.
Is that since the start of the...
For about a minute or so now.
Okay. Sorry, bear with me. I'll just restart it. Is that coming up now? Can everyone see that now?
Yes.
Yep.
Yeah, I see the slides.
Okay, cool. So this was the previous slide that I showed, which shows that I'm sort of focusing on the coincidence region. Yep. Okay, so you can see that. So that's at around 2000 hertz, and the lowest point is around, so 3000 hertz-ish. So this is a plot just showing typical materials that we have in construction industry. So concrete, for example, is the stiffest, heaviest material, and it has a critical frequency that starts at around 250 hertz. And then you sort of go all the way up to your typical plasterboard materials in the region of between 2000 and 4000 hertz. But all of these regions are within the sort of the human ear's most sensitivity. So they're kind of sort of a limiting factor often with systems. So how are we going to tackle this? Well, we've come up with two ideas. One is around shifting the coincidence region beyond the 5K region where it doesn't matter as much, where you're getting already a high transmission loss performance. And through this, we're going to look at multiple thinner layers, materials, and panel surface variations. And then the second is by suppressing or removal of that region using Bragg scattering through small impedance changes, such as pillars or ribbing. And for this project, our test setup remains mostly the same. So we're fortunate here at Auckland University to have a full suite of acoustic chambers. So we have 2 reverberation chambers in the region of 200 cubic meters. So our sample was tested under diffuse field conditions with a 2.4 by 1 meter wall. This is obviously smaller than your typical ISO 10140 wall. It was just because it took a while to make some of the samples, so we didn't want to have to deal with it. But in saying that, windows are tested to 1 square meter, so we think that the results are fairly accurate. So I'm going to start with the multi-thin layers. So this method kind of is based on the fact that if you have a thinner material, then it's more floppy, less stuff. So the critical frequency of that material is much higher. So what happens how can you sort of turn material to have 2 layers of these thin materials? So when they're when it's stationary or when you're lifting it or moving it, it feels like one material, feels like a like a solid material, but actually at higher frequencies, so it acts as 2 thin layers. So you're sort of allowing the shear motion of the material, and so we looked at a couple of patterns, so grid patterns and line patterns, and basically the idea was to investigate how the spacing of blue lines would affect the region, and at what point would it sort of turn into one panel at the coincidence region. And so we used your typical Sally's liquid nails constructed in adhesive, because that's the most common used in the construction industry, with a bead glue line of 3 millimeters. So these are the results from some of these studies, just some quick results. So basically we had 2 layers of 4.5 millimeter MDF. So we're using MDF because it's easier to work with than say normal plasterboard or other products, and its its stiffness is the same in all directions. So you can see here the black line shows, or the brown line shows, a typical 9 millimeter a layer of MDF, and the orange line is when you do blue lines at 100 millimeters, and then the blue line 75 millimeters, and the red line is 50 millimeters. So it's kind of quite interesting that you've shifted the coincidence region right up using this technique, and for all intents and purposes it feels like a solid sheet. We might sort of come into trouble with cutting say jib or whatever if there are 2 layers stuck together. It might be a bit more difficult. You'd have to use some kind of mechanical device rather than a knife slicing it. But as you can see, this is works quite well. So the second technique we looked at was surface variations, and so these panels are basically solid panels, and then we use a CNC router to route out our designs on the panels. So they're 4.5 millimeter deep cuts on a 9 millimeter MDF layer with which are 3 millimeters wide. And we looked at a range of different designs. I can show you. So these 2 pictures here are sort of a square design or a rectangular design, and sort of a checker plate type design. And so I'll show you some of the results from that. So that also, the other picture is showing the panel in the chambers test setup. And so the idea of this kind of system is how can we keep a single material but just reduce its stiffness as much as possible, so that so that it basically shifts its coincidence region up. And as you can see, this is a rectangular grid design, and we've got 50 millimeter lines, 100 by 75, 50 by 50, 100 by 100, and 50 by 75. And the black line is, once again, is just the standard 9 millimeter layer. And you can see we've, in the mass law region, which is the region from about sort of 152 to in the region of 1,000, it's just following mass law, and we haven't really reduced enough material for it to make any noticeable difference in this region. But as you can see, just by putting these routing lines in the panels, we've shifted the critical frequency, especially the 50 by 50 panel, way up to nearly 5,000 hertz. So this also looks like quite a promising method. And the thoughts about this, I'll go back here. The thoughts about this is to try and manufacture these potentially for gypsum while they're still in a slurry state. So you have a roller which will have the imprints on them as they go through the machine and basically create these grooves. And so we also looked at in other designs as well. And the sort of the thought about this was, how can we keep the structural integrity of the material? So we're making them a bit sort of more floppy, stiff, but often plasterboard adds to the rigidity of a building. And so the blue line shows a triangular lattice, which performs really well, but it was clearly, for us, it was clearly the least stiff. And then there's a checker plate design, which was the yellow line. And most interestingly, the green line shows a bullseye kind of design, which the idea was that it would sort of give you all of your angles of all the bending waves at different angles. It would provide a stiffness at all angles. And so once again, the results are really promising, and it's really interesting that the checker design, which feels to be, when you pick it up and move it, it doesn't feel like it's any less stiff than a 9 millimeter layer. Yet it's still producing an improved higher critical frequency. Okay, the last part I want to talk about is our look at Bragg scattering. And I guess this is the hardest to implement in real life, but it's still a really interesting study, and it sort of makes us think about things. So Bragg scattering, as everyone probably knows in this conference, is basically you can have inclusions of changes in density or mass, and you're creating reflections of the waves to create a scattering interference of the waves, and you can create band gaps. This becomes quite a bit more complicated in the diffuse field domain. So we wanted to kind of look at and see, okay, can you sort of create something like this under diffuse field conditions in a panel, and can we target the critical frequency for this? And so what we did is we used some basic kind of construction methods. So we rerouted out a panel with holes and used nuts and bolts for our inclusions in the panel. And so we did a few different designs. So these designs are rectangular. It's a rectangular lattice. So we looked at 45 millimeter square lattice and 15 millimeter square lattice, and using Kirchhoff's plate theory, we calculated what we would expect the band gap to be, and hence designed the lattice size for that.
That's 14 minutes, Andrew.
14 minutes? Okay, cool.
Yeah.
Cool, I will carry on. So these are the results for that, and as you can see, we're actually getting some really good results. So if you look at the 18 millimeter MDF layer, which is the black line, and this shows what you would expect for the same mass, and the red line is your 9 millimeter MDF, and you can see by the blue line and the green line that we're getting out of these high peaks in transmission loss, which are our band gaps, which are quite impressive. We've also done the same kind of technique for a triangular lattice as well, and the idea is that this would be potentially a better way of giving a bending wave at a different angle that would be able to impact into these inclusions more easily or more consistently than a triangular lattice. And the results are kind of similar. You can see the triangular lattice, the 50 millimeter triangular lattice has a large band gap at around the 4,500 hertz, but we're sort of targeting around the 3,000 hertz. And you can see we've actually done. It looks to us like we've got a sort of a band gap there because the critical frequency shape has changed significantly. Yeah, and so this is just a plot of the delta of our best result, showing that you can really improve the transmission loss in this region. So I'll just conclude quickly. Basically, multi-layer panels seem to have a lot of potential, and they feel like a glued solid panel. The router panels definitely improve the coincidence region, but we have to look a bit more at the structural integrity. And the Bragg scattering system produces the predicted band gaps. What's most interesting is, with these point mass systems, keeping the host panel's original critical frequency with the added mass, but the bolts increase the added mass from the bolts increases the mass law. So you've sort of got the benefit of the mass, but not with the stiffness. And so these are the kind of things that we're going to look at in the future, mainly around the static deflection testing of the router panels, and look at finer tuning of the Bragg scattering system to more accurately hit the coincidence region. Cool, thanks very much.
Well, thank you for the very nice talk. We've probably got time for one quick question.